What's up, guys? What's up? I have a plan. Not really. But I want to adjust to a Leetcode problem. So that's what we're going to do. I'm going to do a Leetcode problem. Try and sit up in my chair. Try and have a good posture. And my keyboard's in the office, so I can't type using Vim very much. So let's go. Go to NeetCode. Hello, Geary. You're almost always very, very early. And I appreciate that. It's awesome. Okay. I want to do a graph problem. Walls and gates. Okay. I feel like I'm not going to be able to solve this one, but we'll see. So you're given this. Say, let me bring up OBS. Obsidian, I mean. Islands and treasure. So this is islands and treasure. We're gonna have, yeah, considering whether to keep it light mode. Everything light mode. Since I'm in a white wife beater, maybe I will just stay light mode. How much confident are you with DSA? Let's just say, as confident as the number of questions I do. Right? And I would say, you know, for the questions that I do have learned, I feel more confident solving them. Confident trying to solve them. For ones that are really new, you know, we need more practice on. So it's not always that easy. That's all I'll say. Okay. So copy and paste this. It's going to be a graph problem. And we will go from there. Bhargav got into AWS. Are you saying you? Are you saying you got into AWS? If so, well done, man. Well fucking done. Good shit. I will do one monkey type using just the bad keyboard, as in the Mac keyboard. Ugh. I don't wanna do this anymore. When I don't have my keyboard with me. Because I'm looking down at my keyboard with this, and that's not what we want. I'll tell you what though, maybe I'm gonna get some key bindings up in here on this keyboard. Alright, I'm just gonna say I'm good. Don't worry about that. You're given an m by n 2D grid initialized with these three possible values. It can be -1, 0, or infinity. It can be -1 if a water cell that cannot be traversed. 0, a treasure chest. And inf, a land cell that can be traversed. We use the integer 2 to the power of 31 minus 1 to represent inf. Okay. Fill each land cell with the distance to the nearest treasure chest. Hold on. I'm going to turn down the brightness here. Fill each land cell with the distance to the nearest treasure chest. If a land cell cannot reach a treasure chest, then the value should remain infinity. Assume the grid can only be traversed up, down, left, or right. So given this input, so there's chest 3, 2, 1, 0, 2, 1, 0, 2, 1, 0, 2, 1, 0, 3, 2, 1, 0, 4, 3, 2, 1, 0, 1, 0, and 0. So from a brute force perspective, like if you see an inf, then you know to continue from there. You know to do some sort of searching from there to see if we can reach a 0. And along the way, you can fill in the rest of the board. So then you can end up skipping some of these searches. That seems simple enough, right? That seems simple enough. That seems like the strategy that I would take. Like even with this second example, if you got infinity and infinity, once you see the 1, so if it's not -1 and it's not 0, then you know to make that next one. No, you don't know. You have to do the search. I think you have to do the search, but that means you have an m by n by 4 to the power of k or something. So that's the brute force approach. However, is there any other easier way? If not, so okay. Recommended time and space complexity? You should aim for the solution to be m by n and m by n space. Okay. Let's have a look at the hint 1. Brute force solution would be to iterate on each land cell and run a BFS from the cell to find the nearest treasure chest. This would be a m by n squared solution. Can you think of a better way? Sometimes it's not optimal to go from source to destination. Ooh. Are you telling me to go from destination to source? So the other method would be then to say start from finding the 1, finding the zeros. From the 0, look from the outside and see where you can expand out. Right. Then you go, okay, expand out 1, 1. That's it. And then you expand 1, and then that's it. Can expand 2, draw, expand 2, yeah. But it's almost that you keep it in a BFS. And then you continue expanding the 3s. You only expand the 3rd if you know the surrounding is a 2. If you know there in the surrounding there is a 2. And then what would this time complexity be? It would be O of m times n. It would be O of m times n. I see. Okay, let me just look at the second hint here. We can see that instead of going from every cell to find the nearest treasure chest, we can do it in reverse. We can just do BFS from all the treasure chests in grid and just explore all possible paths from those chests. Why? Because in this approach, the treasure chests self-mark the cells level by level, and the level number will be the distance from the cell to a treasure chest. We don't visit a cell. This approach is called multi-source BFS. How would you implement it? So this is multi-source BFS. For sure, no, for sure. It's because it's multiple sources. I can see how that works. I can definitely see how that works. Okay, hint number 3 though, I feel like would help us determine it even further. Okay. Alright, yeah, so I'm not going to look at the third hint there, but I think I know what to do. So, let's think of what we need. From collections, import DQ, because we're going to use a queue. We're going to set the queue. So it's going to be a queue DQ of an empty set. And for row column, wait, so rows is equal to length of grid calls, wait, let me see, rows, length of grid calls is equal to len of grid 0. We can assert that. That was Siri. That was really loud. What's up, Big? We got a cat. We got a cat here. Hold on, I'm getting distracted by a kitty. Big is here. Big over here. Alright. Hear herself. Yep, you see a cattail. Oh, she's just butting her head into... Oh. Yep. There she goes. Yes. The fig. Wait. Yeah. Ooh. And just eating everything. Oh. Huge fluffy tail. Now she is up on it. Yo. Cat. Heading. Pig the cat. Pig the cat. Pig is like, gonna get down now. Just chilling. Okay. Alright, so we said m and n has to be greater than or equal to 1. Alright. For row in rows, for C in calls, grid of row call, if this is equal to 0, right? So this is 0, but is this... No, it's completely an integer. Yeah, it is an integer. So if it's 0, then q dot append, we add the row and column. Let's see. We add that row and column, and we don't need to update the grid. It'll be 0. Okay. While q does not equal to empty, we're gonna q dot append at some point. We're gonna q dot pop at another point, where we pop from the queue to get the said row and column. I can just keep this R and C, I think, and then we append some new R and C that we're gonna figure out. So from 0, we're gonna have dirs for directions. It's gonna be a tuple of directions. I'm gonna go right 1. I'm gonna go left 1. I'm gonna go up 1. And we're gonna go down 1. Okay. For here in, so tr bc in steers. So for each of the directions, this is where we have to think. So if the direction that we are currently concerned with, grid it's like in my suitcase right now. What are you doing, Fig? Around? Still there. You can actually just chill where it currently is. Big yawn as well. Yawn. Back this way. Okay. I need a cat in my life. This is the roommate's cat. What's Fig doing now? Like buried in my suitcase. Fuck shit. Hello, man. Row plus d row. Column plus d column. If this is not equal. Okay. Here's the condition. If it's not equal to -1, we're gonna somehow add these. Grid RC equal to is equal to 1. What are we thinking? Grid RC plus 1. So what this says is that if it's not water, if it is water, then you wouldn't do anything. You wouldn't check any further. But if it's not water and the grid at your current position plus 1 is smaller than grid DRDC, next, then you would set grid DRDC to this. and then you append, and then you return grid. Int object is not iterable. Right, in range of rows. Can't forget that. In range of calls. Now list index out of range is also, yep, definitely a possibility. We've got to ensure if grid of, if r plus tr, if 0 is less than r plus tr, and r plus tr so less than equal to is less than rows minus 1. Or should I say less than equal to rows minus 1? I know I'm writing more by doing it this way, but it's clearer to me what's happening. Ugh. And if I not all of this is what I have to do as well. So if I not all of this, then you have to be is less than 0 or is greater than rows minus 1, less than 0, greater than rows minus 1, if it's greater or equal to, fine, and column plus t column less than 0, or column plus t column is greater than cols minus 1, you continue. Alright. Still index out of range. Line 30. Line 30. That's not right. Let me think for a second. Okay. It may be that we need to add these. Wait. Pop from an empty does not equal to empty. While Q... Wait. But this is right. While Q... While Q, I suppose. The output was 3, but the expected return type is none. None. Well, there you go. Accepted. Let's go. Let's go. That's a big W. Except I will say, what does this look like for the Leetcode problem? I'm also 20% on my phone. No. To subscribe to unlock problem? God damn it. Okay, but I think this is what I did. I think this is correct. However, I will just double check. Like by watching these videos. I will copy these though. Put these into LeetCode. repository. So Alacrity, oops, Alacrity, CD, let's see. Let me move these, clear. Hello Nahi. How's Amazon? It's great, man. If anything, you should be asking me how's Sydney. Because I will say, like, beyond Amazon, there's also a lot of events that I had for like with other interns, other friends, other new people that I've met. It's been a lot. It's really been a lot. So it's been great. It's actually been great. Both at Amazon and just in Sydney in general. I mean, yeah. I mean, look, if you have questions, ask away. I'll try and answer them. I will say I have made use of sorry, I have made use of command line a lot more at Amazon, because I'm trying to run services, and that's the best way to go about things, using the terminal. So peak, I couldn't enjoy terminal life any better, anymore, with the tools that I've learned over my time just being by myself. Like, it's come useful in the Amazon work that I do. Walls and gates. So 286 walls and gates. 286 walls and gates. .py. Okay, and we can paste. Let's just create a new line for this. Are we satisfied with that? I think so. I think that's all. I think that's all she wrote. Quits. Okay, git add, git commit. We're gonna add solved problem after looking at hints, but this was pretty easy, I will say. Git push. Okay, and Obsidian. So solved this problem after looking at some of the NeetCode hints. Biggest hint which helped was to look from destination to source rather than source to destination during a BFS. Now I can do S. Alright, that's easy. Okay. I want to try and see if this is solvable. Link to all problems. Problem solution. Okay, well, I'm not going to read that. What I will read instead, what I will watch is NeetCode solution right now. Now I hope it's pretty similar.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve another graph problem, walls and gates. So we're given an m by n grid where each position could have 3 possible values. A -1, which represents a wall, aka an obstacle that we're not allowed to visit. We're not allowed to visit these walls. A 0, which identifies a gate, so this is an example of a gate in this case. And the third value is infinity, which basically represents an empty room. And basically for every single empty room, aka every position that's marked as infinity initially, we want to identify what's the nearest gate to that room, and then we want to take the distance from that room to the nearest gate and then replace that infinite value with it. So, and if it is impossible, basically if an empty position cannot reach a gate in our graph, then basically we're going to leave that position as infinity. So for example, let's take a look at this example. The easiest one over here, right? How far away is this empty room from a gate? Well, it can go in 2 directions. It can go down, which is an obstacle, so we're not allowed to travel in that way. We can't go up or to the right, those are out of bounds, but we can go to the left, and of course, right next to it happens to be a gate. So what we're going to place here is a 1, meaning this is 1 position away from a gate. And similarly, this one, how far away is this from a gate? Well, 1, 2, 3 positions, right, from a gate. So we could put a 3 here, we could put a 2 here, and a 1 here. What about this one? We could go 1, 2, 3. So it's 3 positions from this gate, but it happens to be that there's a closer gate if we go to the right and then we go up, right? So the closer gate is actually 2 places away. So we're going to put 2 in this position. And now what happens if there was a gate over here? What would we mark these 2 as? Well, basically they start out as infinity and we would leave these 2 positions as infinity. So any positions that cannot visit a gate are going to be remaining as infinity. So the first idea that you might have for this problem is basically for every position we want to know what's the closest gate. Why can't we just run a DFS, right? Basically a DFS until we reach the gate, or, you know, we reach as many positions as we can. We return what was the closest gate to that position, right? And then do that for every single position in the entire grid. Now, what's the time complexity going to be of that?
Damn, I really
well,
did
a
the
DFS
best
is going to
solution, I
basically
think.
be the size of the grid, and we're going to do that for every single position in the grid.
That's
So
good
basically,
to
it's
have
going to be
the
something
hints,
like
I will
m
say.
by n squared. So the question is, can we do better than this big O time complexity? Well, let's try out a BFS solution, right? We tried DFS. Let's try out breadth first search and see what that leads to us. Let's say we started our BFS at some arbitrary position like this one. Is it possible that we can eliminate repeated work if we do that? Well, we're going to start here.
And I
and
got
then
the
visit
solution
all 4
pretty
directions and see
simple
you know,
looking.
what's the closest gate that we can get to.
19
So starting
lines.
here, we have a distance of 0. It takes us a distance of 1 to get to these positions. And then finally, we can get a distance of 2 to get this position, right? But since we don't want to revisit the same node twice, the same position twice, we're going to do exactly that. Once we get to a position, we're going to leave it as visited. So, if we go from here
It's
to
well
here, it
thought
takes
out,
us 2 positions.
I will
so,
say
then we
today
can say, okay,
for
for this
my-
position, it took us 2. But when we go up, right, we get to this position, we can't really
my
go in any
solution.
other direction. So basically, this is going to be remaining as a dead end. We're never going to get a distance in this position, right? Because we don't want to revisit the same position twice. We can't go back in the direction that we came from. So a BFS solution starting from the rooms is not going to work if we want to get an actual O of m by n solution. It's not going to work if we do it from the rooms, but let's reverse our thinking a bit. Why don't we do a BFS solution from the gates? So for example, from this gate, we can say, okay, let's mark all adjacent rooms basically as saying, okay, all of the adjacent rooms are 1 distance away from this gate. And then let's continue that. So from, this room doesn't have any other rooms adjacent to it, but this room does. So we can say, okay, for this room, it's 2, and this room, it's also 2. This is 2 positions away from this gate. And we continue, right? We say, okay, this room is 3, and continue from here. This room is 4, and from here, similarly, right, we'd say, okay, this is 3, this is 4, and this is 4, right? But is that actually true? Is this room 4 positions away? Well, we forgot about this gate, right? So a better way of doing this would be to simultaneously do a BFS from both gates at the exact same time. So in that case, if we ever reach a
This is like
position. So
perfect.
let's see what happens when we do a BFS simultaneously. So from here, we're going to say this is one, these two are one position, and this is also one position. Now from all of our ones, we're going to continue the BFS, right? So from this one, we'll say these rooms are 2 away. From this one, we'll say this room is 2 away, right? Now from this room, right, this is 2 away. We're not going to go to this position and say that it's 3 positions away, because this has already been visited. We've already found the minimum distance that this is away from a BFS, right? So every time we expand one layer, we're saying, okay, first let's find all the rooms 1 distance away from a gate. Next, let's find all the rooms 2 distance away from the gate, and 3, and we keep doing that until every single position in our grid has already been visited, or we basically cannot continue. And we know BFS solutions are implemented with a queue, so once our queue is empty, that's how we know we can stop. So let's just continue a little bit more. So from this 2, the only unvisited neighbor is this one, so this is 3 positions away. This one is also here. So now we're going to do a BFS
Perfect.
from the remaining 3s. We can see only
Very
this
good.
3 actually has a neighbor. So we'll say this one is going to be 4. And when you take a look at the actual output that they built, our solution exactly matches what they did. And we didn't have to revisit the same node twice. All we had to do was initialize our queue with the 2 initial positions for the gates.
That's very good.
And then expanding outwardly, basically incrementing the distance every time we complete a full layer of our BFS traversal. And that actually led to us having a time complexity of m by n. We're also going to have that as the memory complexity, because we're going to have a visit set to make sure we don't visit the same position twice. But once you kind of know that this is going to be a BFS from multiple sources at the same time, implementing the code is pretty straightforward if you know how to do BFS. So first things first, let's get the dimensions of our grid. So the number of rows and the number of columns. I usually like to do this at the beginning. And we're also going to have a visit set that is going to make sure that we don't visit the same position multiple times. And we're also going to have a queue, which initially lets
I gotta see how he means by
empty,
O
but
of
we're going to initialize that with the
M by
gates
N
first of all, right?
space
So
complexity.
now let's go through every single position and actually initialize our queue, right? And we know we're just going to do that with the gates. So we're going to have to go through the entire grid. So
He has a
iterating
visit
over
set.
the entire grid. And even though we're doing this, it's not actually going to change the overall time complexity. So we're going to go through
Right,
every position.
that's the biggest
If
problem. It's because he
rooms
has a
at
visit
this
set. I
position
don't.
is equal to a gate, meaning it's equal to a 0. Then we're going to add it to our queue. So we're going to say queue.append this position. And let's make sure to add it to the visit set, because we don't want to have to visit this same position twice. And now we can actually start doing our BFS. So initially the distance is going to be 0, because we're going to be popping the actual gates first of all. So we're going to say while queue is non-empty, we're going to go through every single position in the queue currently, right? Basically this layer of the queue. And so we're going to be popping from the queue. So pop left from this queue, we're going to get the coordinates of the gates that we initially added, right? That's going to be the first layer.
Am I
The
doing
first
this in
layer we're gonna be
BFS?
popping are the gates that we just added, right? So for each gate, we're basically
I
gonna
did this
say,
in
okay,
DFS.
let's change this gate to being the current distance. So since the current distance is initially 0, and remember the gates start out as having a value of 0, we're not actually going to be modifying the value of the gates.
Wow.
But the reason I'm putting this line here is because after we pop the gate layer, the next layer that we're going to add to our queue is going to be
In
all
reality,
the
it doesn't
rooms
matter.
that are 1 distance away. So after this for loop, let's make sure that we remember to increment our distance by 1 every time we complete a full layer of the queue. And so basically for this room, let's just go ahead and add room. We're going to add every single neighbor of this room. And you can see I haven't actually defined that function yet. So let's do that up above once I actually write this out. So basically what I'm doing is going to be adding all 4 adjacent rooms to the queue. And we obviously know that some of these rooms might be out of bounds. Some of them might have already been visited. That's why I'm going to put this in a helper function to basically abstract some of that logic for us. So let's define
This
the
is just,
function up
yeah,
above.
his
over here.
solution
So
is
add room,
slightly
we're just gonna
overly
pass in a
complex, I
couple
will say.
coordinates. So basically, if this row is less than 0, or if the row is out of bounds, meaning it's too big, meaning it's equal to the number of rows, or the exact same thing for column if column is less than 0 or column is too big, or if this position row column has already been visited, or one last condition, basically if this room is a wall or an obstacle, right? Because remember, not every position in our graph is a empty room. It's possible it could be a obstacle, meaning it's equal to -1. So if any of these above conditions is true, we're going to immediately return.
Oh, well, that closed this.
Hey everyone, welcome to the queue or the visit set. But if it's not invalid, that's when we can go ahead and say, okay, visit.add to the hash set and go ahead and queue.append.
Yeah, you don't need the visit set.
Well, right? So basically you can see why I'm putting this stuff inside of a helper function, because we don't want to have to call that 4 times. And I don't really want to put a loop in here because I just think it's kind of messy. I'd rather just write it out like this. But so with all of that done,
from my understanding,
we have added the rooms. Okay. We're making sure to increment the distance every time we complete a layer. And we're basically going through rooms, labeling what's the minimum distance from that room to a gate. Once we're done with that, we don't actually have to return anything because we just have to modify the room's 2D array in place. So this is all the code that we're actually going to have to write. So you can see that this solution is efficient. We're basically visiting the entire grid a couple times, I think 2 or 3 times, because of course we have this initial loop and then we actually have to run our BFS solution, but it's still a linear time solution with respect to the size of the input array. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot.
All right, we're done with this problem and we're done with today. I'm gonna go eat dinner. I'm gonna go out some dinner. All right. Thank you for sticking along, guys. Appreciate you guys sticking along. Next one, I hope to do more. And it'll just mean I'll have to do less events, because I've been going to a lot of events over the past. I haven't been at home properly to eat dinner for 6 of the days, so I haven't had much. I haven't done much. Anyway, done much Leetcode, that is. Alright, anyway, thank you guys. Thank you Nahi. Thank you Rishi. I'll see you guys sometime soon. To be decided. Alright. Cheers. Peace.